In this section, we will discuss the confidence interval for the single population mean when we do not know the standard deviation. In that case, we will use a different distribution that is called the student's t-distribution. As a reference on the Introductory Statistics textbook by OpenStax, this is section 8.2. In the Lumen Introduction to Statistics Corequisite book, this is in Module 8, Introduction to a Single Population Mean, using the student's t-distribution. And in Art of Stat, instead of using the normal distribution app, we will be using the t-distribution app. So let's talk a little bit about what happens when we do statistics, but we in fact rarely know the population standard deviation. So what we do is we use the sample standard deviation as an estimate for the population standard deviation, and we proceed as before to calculate the confidence intervals that we have more chances for error. So we have close enough results depending on the sample size. So if our sample size is n, we said that is n and it's greater than 30. We discussed when we were talking about the central limit theorem and the law of large numbers that as the n increases, then the distribution of the sample mean becomes more and more normal. So statisticians ran into problems when the sample size was small. A small n caused inaccuracies, and a gentleman called William Gossett ran into a problem as he was working in his brewery, and just replacing sigma with s did not produce accurate results. So what he did is he realized that a normal distribution is actually insufficient for this calculation. The distribution depends on the sample size n if I want to have a correct distribution. And through this situation, when he was trying to resolve, he discovered what is called today the student's t-distribution. The name comes from the fact that Gossett wrote under the pen name student. Up until the mid-1970s, some statisticians used the normal distribution approximation for large sample sizes and only use the student's t-distribution for small sample sizes that were at most 30. But now with technology, we can use the student's t-distribution for any sample size under the condition that we do not know sigma and we use the standard deviation of the sample S to estimate the standard deviation of the population. So what is the student's t-distribution? If we draw a simple random sample of size n that has the population has an approximately normal distribution with a mean mu and an unknown standard deviation, the t-score for that sample is x bar minus the mean divided by the standard error s over the square root of n. Remember, s is the estimation of sigma. So if the standard error before was sigma over square root of n, now we have an estimation for that standard error s divided by the square root of n. For every sample size n, there is a different student's t-distribution. The student's t-distribution depends on something that we call the degrees of freedom. Degrees of freedom is the quantity n minus 1. If you remember, we saw that in the denominator of the calculation of the sample standard deviation s. Because the sum of the deviations of a sample equals to 0, you can find the last deviation if you know the other n minus 1 deviations. These n minus 1 deviations can vary freely, and that's why this value n minus 1 is called the degrees of freedom. This is how free you are within your sample to not know your deviation from the mean. The graph of the student's t-distribution is similar to the standard normal curve, so it looks normal. Let's take a look here. So as you see, it looks kind of a normal distribution. This graph that automatically comes in Art of Stat has a distribution, has degrees of freedom 4. 4 is n-1. That means that the sample is 5. But as you change the n, the distribution changes. So as I slide the slider, my distribution changes. As I move it, the distribution changes. And that says that for every different degrees of freedom, different n, I will also have a different t distribution. The distribution also looks like a standard normal curve. So if you pay attention here, the mean in the middle is 0. And then we have tick marks for standard deviations equals to 1 each one. So I go by ones to the right and by ones to the left, and the left has negative t-scores and the right has positive t-scores. It is symmetric about the mean. It has more probability in its tails than the standard normal distribution. So again, if you pay attention here, it doesn't go only 3 tick marks to the right. It goes more than that, and there is area under the curve. If you go beyond the 3 standard deviations, remember that in the normal distribution, the empirical rule says that 99.7% of the data will actually lie within the 3 standard deviations from the mean. This is not true for the t distribution. However, as you increase the sample size, then it does look more normal. So now I have gone above 30 for the sample size. In this example, the degrees of freedom are 31. That makes the sample size equal to 32. And if you pay attention here, it looks like most of the data is between -3 and +3 from the mean of 0. So the exact shape of the student's t distribution depends on the degrees of freedom. As the degrees of freedom increase, then your graph of the t distribution will become more like the graph of the normal distribution. The underlying population must be normally distributed, especially because usually you will not have large enough n. You will not know the mean and the standard deviation, so you will be creating a confidence interval using your sample mean as your point estimate and the sample standard deviation as an estimate for the standard deviation of the population. The size of the underlying population is generally irrelevant unless it is very small. If it is a bell-shaped normal population, then the assumption is met and doesn't need discussion. Random sampling is assumed, but that is also a completely separate assumption from normality. And the notation for the variable following a student's t distribution will be the variable t, which is a t-score, will follow a distribution t with degrees of freedom df equal n-1. So in this example over here, I would say that this variable follows a t distribution sub 31, and 31 will be the number of degrees of freedom that will indicate a sample size of 32.